This lesson is on solving a system of linear equations by substitution. So substitution is the tool that we will use to solve a system of linear equations. So far we've only looked at solving a system of linear equations graphically. So let's solve the below system of equations by substitution. We have x plus y equals -5 and x plus 3y equals -15. Step 1. When solving by substitution, pick one variable in either of the equations and isolate it. If any variables don't have a number attached to them, be smart and pick one of those variables. The x would work in either equation for this specific system of equations because you can see there is no number attached to the x. This will make isolating the variable one step faster. Let's label the equations a and b, and let's isolate x in equation a. So all I did was move the y to the right hand side, so I subtracted y from both sides to keep the equation balanced. Didn't actually want to change it, but we got rid of the y on the left hand side because we subtracted the y there, and we have a negative y on the right hand side now instead. So we have isolated x. Now step 2. This is where this method gets its name. We substitute this isolated x variable into the other equation b. It's very important to sub it into the other equation, not back into its equation. If you subbed it back into itself, you would just get, everything would cancel. You get 0 equals 0 and not make any progress. So wherever there is an x in equation b, plug in -y minus 5 in its place, and always do this in brackets. So let's do that now. So you can see this is equation b here, but where we had an x, if you see my cursor, we have put -y minus 5 instead within brackets. And now you'll see that we have one equation with one unknown. One equation here, and our one unknown is a y. So we can solve for that one unknown. We want to isolate or solve for y. So 3y minus y is 2y, collecting those like terms, and then we just have the -5 still, and -15 on the right hand side. And then I've moved the -5 to the right hand side by adding 5 to both sides. -15 plus 5 is -10, and we got rid of the -5 here by adding it to this side. And then finally, we need to get rid of this 2 stuck to this y, so we divide both sides by a 2, and we get y equal to -5. So continuing from the previous slide, we had found that y is -5 in the below system of equations. Step 3, plug this known value of y into the isolated equation. So that was the equation up above, this one here, x equals -y minus 5. You could also plug it into either one of the original equations and solve for the unknown x, but it's fastest to plug into the isolated version since you did that work already to isolate x. Now we just plug in -5 for y here. And so this was actually another kind of substitution here. We substituted the value of y in, of -5 in for y. And so use brackets again. That'll make it simpler when you need to deal with negatives. So negative times -5 is just +5 here minus 5, and x equals 0. So finally, we have x equals 0 and y equals -5. Those are the x and y values that satisfy both equations a and b above. So if you plug x and y, x of 0 here and y of -5, you'll see that goes to -5, and x of 0 here and y of -5 here, you'll see that that goes to a -15 there. So that's an easy way to check. Did you get the correct solution here for the x and y values? Do they satisfy both of these equations? Let's solve the below system of equations by substitution. So again, pick one variable in either of the equations and isolate it. Let's label the equations a and b. Let's isolate x in equation A. So unfortunately there's a number attached to every one of the variables here, so I just chose x in equation A because it has the smallest number attached to it. It makes it a little easier in the end. So we're isolating x now. So I move 3y to the right hand side, divided both sides by 2. Negative 3 divided by 2y plus it was 8 divided by 2, which is a 4 there. So we've isolated x now. So step 2, substitute this isolated x into the other equation b. So again, wherever there was an x in equation b, we put big brackets now and what x is isolated as from equation a. So we plugged all of this in for x over here. And you'll see again that we only have y variable here. And it's one equation. So we can isolate that y variable and find out what y is equal to. So we'll isolate that y. So expanding out our brackets here, we have 5 times minus 3 over 2y is 5 times negative 3 is negative 15. And then it's like there's a 1 underneath here. There is a 1 underneath. So 1 times 2 is just a 2. And then y. And then 5 times 4 is 20. And then our minus 4y stays the same. Minus 6 stays the same. I moved the 20 over to the right hand side, so subtracted 20 from both sides, keeping the equation balanced. We want to get y by itself, so get everything else to the other side. So this became a negative 6 minus 20, a negative 26 on the right hand side. So there's different ways of dealing with this fraction here, but the way that you should know is we can make this 4 have a common denominator of 2 over here by multiplying top and bottom by a 2. So we get 8 on the top, the bottom becomes a 2. Now we have a common denominator. Now we can combine the negative 15 and the minus 8 to be a negative 23 in the numerator, our common denominator of 2 times y equals negative 26. So I did that to combine these two terms. And now, I don't like fractions, so I will multiply both sides by 2 to get rid of that 2 down there. And I get negative 26 times 2 is negative 52. And then finally, we don't want that negative 23 stuck to that y, so we divide both sides by negative 23, and we get positive 52 over positive 23 because those two negatives canceled. So make sure you can follow the algebra there in isolating y. Feel free to pause the video right now, just to make sure you get all those steps. Continuing from the previous slide, we found that y equals that in the below system of equations. So step 3, plug this known value of y into the isolated equation, where we isolated x in equation A. So that was our isolated equation. We know y is 52 over 23, so we plug that in for y. And then I did a little bit of simplifying here. 52 over 2 is just 26 over 1. And then negative 3 times 26 is negative 78. 1 times 23 is 23. Plus 4. And we want to combine those. How do we do that? We need a common denominator of 23 for our 4 value here. So that becomes 92 divided by 23, because we multiplied that 4 by 23 divided by 23. And now we have our common denominator, and we can add the numerators. So we get x equal to 14 divided by 23. So finally, we can say x equals 14 over 23 and y equals 52 over 23 are the x and y values that satisfy both original equations. These original equations A and B here. This equation here, this equation here. So again, you can check by plugging both x and y into each of these equations. And so if you plug 14 over 23 for this x and 52 over 23 for this y, you should get 8 when you multiply that out. And same thing here, if you plug those values in here, you should get a negative 6. Solve the below system of equations by substitution. Again, step 1, pick a variable and isolate it. Let's label the equations A and B. Let's isolate x in A because x is already kind of by itself. It's just negative. We need to make that positive. So I'll move x over to the right-hand side, 8 over to the left-hand side. We get 5y minus 8 equal to x. Step 2, substitute this isolated x into the other equation b. So wherever there's an x in that other equation, we're going to use 5y minus 8 instead for that value of x. And we do that so that now we only have a y in this equation, and we can isolate or solve for that y. So multiplying out this bracket here, we have 2 times 5y is 10y. 2 times negative 8 is negative 16. Carry down the negative 10y and the 7. And this is very interesting. 10y minus 10y is 0. Your y's actually cancel out. They go away. And then I move the negative 16 over to the right-hand side, which became a positive 23. And so we got 0 equals 23. Okay, something seems to have gone wrong. 0 obviously does not equal 23. So first thing you want to do is go back and check if any mistakes were made. Everything looks fine. Let's rewrite both original equations into slope-intercept form and see if we can figure out what's going on here. So rewriting A into slope-intercept form, we have that. And rewriting B, we get that. You can pause and make sure that you see the algebra I did there. So do you notice anything about both of those equations A and B in slope-intercept form? Well, they have the same slope. M is 1/5 here and M is 1/5 here. If they have the same slope, will they ever intersect? Well, no. Specifically, if they have different y-intercepts and the same slope, those lines are parallel, and they will never intersect. So no wonder we got a result that didn't make sense when trying to find the intersection point. Both of those lines are parallel, they will never intersect, so when you try to solve that system of equations, find that intersection point, feel free to go back to the previous lesson on solving systems of equations graphically to see what I mean. Yeah, we don't get an answer here. We get a nonsensical answer. So the answer to this equation is, you would say just there is no solution. So quickly here, there are 3 different types of solutions for a system of 2 linear equations. There, as we just saw, there isn't always a solution. There could be no solution. So type 1 is there is one solution of x and y, corresponding with one intersection on the graph, one intersection point. So this is an example here. We got 2 lines and they intersect at one point. If you wanted to solve it by substitution, algebraically, you would get the x and y coordinates here. Or you could solve it graphically, as I showed in a previous lesson. So this is one type. This is the first type we saw. There's the case with no solutions that we just saw, since the lines would be parallel and they would never intersect. So that's this type over here. You can see that those lines are parallel, they will never intersect, therefore there won't be a solution. If you tried to solve it algebraically like we just did, it wouldn't make sense. And then finally, the third type is there are infinite solutions. And this happens if the lines are actually exactly the same line. And it might not be really obvious. It's relatively obvious, but not really obviously, because I'll show you on this next slide here. How could this happen where it's not obvious? Well, they could give you a question like this. They don't actually give you the exact same numbers in both questions, but you'll see here that the second equation is the same as the first, except every term is multiplied by a 3. So we have y times 3 is 3y, 2x times 3 is 6x, and 5 times 3 is 15. So can we actually prove that these are going to be the same equation? Yes, we can. Let's isolate y. So it is best practice to always factor before canceling. For our equation here that we want to show is the same as this one, we're going to factor out a 3 on the right-hand side. And so we get 3 times 2x plus 5. And now you can divide both sides by 3. And what do you get? You get y equal to 2x plus 5. Or what you could say is, I want to get rid of this 3 on this side, so I divide both sides by 3, cancel it on this side. Well, then it goes over to this side, and you're dividing by 3 on the left-hand side, and then it'll cancel with that 3 as well. So you'll get this. And that is, yes, exactly the same as the first equation up here. So you've shown with just a bit of factoring and canceling that you've proved mathematically that those are the same equation. So that is actually the end of that lesson.